Yep, should be recording, I hope, Cass.
All good. So let's kick on. So thanks for coming tonight, guys. We've decided to try and have a bit of a series of webinars about just things of interest. Things that are important to you, but and you're getting a lot of information on. But there's just a few areas that we reckon there's a few little gaps that we might be able to help support with. Hence why we're here tonight. So before we kick off, I'd just like to introduce the rest of the Cool Soil team here on tonight. So maybe, yeah, quick intro, starting with Harry.
Yes, so I might be a new face to a few, but I've probably spoken to you on the phone or something. Yeah, my name's Harry. I've come onto the Cool Soil team as an agronomist based out of Wagga. So, yeah, sort of servicing the Riverina or the Old Farm Link region and yeah, the Central West. So, yeah, looking forward to getting to know everyone and yeah, hoping this webinar series can be of some benefit. Well, the next one will be on some nitrogen management and inhibitors and the role they play. Then there'll be one on biologicals and biostimulants and I suppose the difference, where do they have a fit? And I suppose from Cass's end, what's actually got some evidence behind it and has a fit in our systems. And then I am working on doing a fourth webinar as well. So we'll see what the topic of that one is yet to be. It might be on something on the sustainability reporting end or something as well. So we'll work on that one in the background and keep you guys in the loop. But that'll be probably more August time or something a bit later, a bit deeper into the year. So anyway, yeah, nice to see you all, and yeah, looking forward to tonight.
All right, Sarah.
Yes, hi everyone. I think I've met a few of you, but I'm the soil scientist with Cool Soils, so work with Harry and Cass and Rena. My main focus is our innovation trials. So if there's something that you want to try and you like want a bit of help with design of maybe an experiment, maybe it's lime or legumes or something like that, that's a bit novel or something that you haven't tried before, like we've done a few fertilizer enhanced efficiency fertilizers trials in the last few years. If there's something you want to try, I'm happy to have a chat and talk about it. But that's kind of where I fit with Cool Soils.
Thanks, Sarah. Norena.
Hi everyone. My name's Rena Cooper and I live in Rutherglen, not far from Cass. And I'm the field services person that looks after the region. It's called the Murray region, and that sort of extends from Shepparton right through to Henty, bit south of Wagga, and as far west as Berrigan, if not a little bit further. So I look after that area, and I've been out soil sampling today, haven't we, Jane? One of my farmers are online too. So, yeah, really enjoying it. Thank you.
Thank you, Rena. All right, so I've got a bit to get through tonight, so we might crack on. If there's any questions as we go, feel free to somehow let me know. Maybe, Harry, if you can keep an eye on the chat or whatever, and we'll see how we go. Fingers crossed. Harry, can I please share? Thank you. Gotta love a bit of tech. All right. All right, so tonight we're really focused on soil tests, what the numbers are in them, and then kind of what they mean. Because what we know is that you guys spend a lot of money on soil sampling. Soil testing is a key part of what we do in Cool Soil as well. And there's always these soil test results coming through. So just thought it was a good chance just to have a bit of a chat about what all those different numbers on the test mean. And if you've got any soil tests yourself, either from Cool Soil or from other sources, feel free to play along. It's a game we can all play. So what we'll talk about today is, first of all, soil sampling, just a bit of a refresh on what all that looks like, and then breaking down the soil tests and what's in them. I was optimistically looking to have a bit of a chat about what biological products there are coming through right now, but I don't think we're going to have time for that one, so I prefer just to focus on the soil sampling piece. And for those who I haven't met and I've met most of you. My name is Cassie Schaefer. I'm the principal scientist for Cool Soil, and I've been in the soil science research space in soils for about 20. This is my 26th year. So I think I've officially hit old fart status. All I need is the brown jumper and the was it the sandals and the long socks? I think was the old soil scientist gig. So stay tuned. See how we go with that one. All right. So first of all, with site selection, this is something that has really evolved, really over the last 25, 30 years. And so just to kind of refresh on why we do what we do with our soil sampling. So we've historically used what we call transect sampling, which is kind of doing across from one end to the other, either as a straight diagonal across a paddock, or we do pretty patterns, or we do W's or X's, or, there's been a whole raft of different things that are done. And this was originally done on the basis of trying to capture the whole paddock, in a sense. What we know now is that's actually really poor for tracking change over time. So while it gave us a number that was kind of an aggregate or an average of the paddock, because there is so much variation in the landscape that we really didn't appreciate, even 20, 30 years ago, that all that variation actually then cancels out any of the changes that we might be making. So we actually now believe this is one of the key reasons why we weren't able to pick up good increases in soil carbon levels when we went from our conventional cultivation through to our no-till systems and our stubble retention systems, because of that variance across the paddock. So we do our transects, we'll get our numbers, come back a few years, do it again, and there's just so much error or variation there that numbers just weren't lifting. So really poor for tracking change over time. If you're looking just to get a bit of a gut feel of what's happening, and if you have a good history of doing that and it's been done in a consistent manner year on year, then don't throw everything out. But if you're setting up new sampling approaches, then we certainly wouldn't recommend that transect sampling is what's done. So in these days of smartphones and satellites, there's really no reason why we can't do GPS located sampling. And the beauty of that is that we go back to the same point time on time. So there is this conflict a bit on the fact that we went from doing a kind of whole of paddock approach through to a certain selective sites in a paddock approach. And where we come down to is that there's no perfect way to go. But if a key part of what we're looking to do is to capture the range of variation in paddock, or to pick a site that reflects, our average conditions, or, the dominant part of the paddock, then those selective points really work. So when we're choosing our GPS points, we're either talking about what's a part of the paddock that's most reflective of what's happening, and that's when we rely on satellite imagery and farmer knowledge of what's happening, or we're looking to do our best and our worst areas. So as a minimum, we're kind of looking to say, if we're soil sampling because we want to understand what's constraining our system, then we really need to do that, what we call bookending. We pick our best parts of the paddock and our worst parts, or our most different parts, and GPS locate from there. That's also working on obviously reflecting limited budgets and everything else. If budget's unlimited, go forth and do lots. The more samples in a paddock, obviously, the more confidence you'd have around the data that you're collecting. I get asked a lot about grid mapping and grid soil sampling, and this can be a really good tool to understand what's happening in our surface level variation. The challenge with grid mapping, though, is if that's all you're doing and we're just getting those 0 to 10 numbers, because we get some really pretty pictures with that, we get a prescription on how to solve it. It's really easy to look at that and go, well, that's all my problem. I'll work off those prescription maps, I'll do the variable rating, and job's done. What we find, if that's the approach that's taken, there can be a lot of things happening just underneath the surface that aren't reflected in that. And so there can be kind of accumulated subsoil acidity, for example, and we're not picking it up. So to get the best out of grid mapping, to combine that with some selected deep incremented sampling is really high value, because then you get that variation on the surface, and then at, maybe 2 or 3 points in the paddock, what's happening in those deeper layers, which are also GPS, so that you can track those over time. But a lot of our soil sampling does come down to what we can economically justify, but there's a lot of different tools that we can use that then give us different learnings from that. So it's really around what we want to achieve with our soil sampling to what we'll get out of it. So just an example of how much things can change in a paddock. I've just got an image here of a very uniform paddock. So when we looked at this paddock, it was flat. Nothing really changed. The soil type didn't change on the surface. Colour didn't change on the surface. There wasn't big differences in that paddock. But when we went through and did specific soil carbon sampling through that paddock, and this is a paddock that we used to actually simulate what carbon stock sampling looked like for a carbon project, but that's another story. But we actually sampled these polygons according to variations in hyperspectral imagery. So what's different in that paddock? So what we can see here is that these soil carbon values, which are carbon percents in our 0 to 10, they change quite a lot. And so you can see if you were to do a transect through there, you'd get an average number. But because we've got such large differences there, it's very unlikely to be able to pick that up, change over time. In comparison though, if we were to select discrete locations in that paddock, we wouldn't be seeing that whole uniform story, but we would see how certain points then changed with different management and time that we imposed. The other thing around soil sampling is actually how we manage and handle that soil, and then how we get it analysed. So the key, very simple things are around using standard methods. So there's a reason why we all do the same thing when it comes to soil sampling, and that's because if we all speak a common language, then we can actually build on the learnings that we've had from past years, using standard methods to ensure that we can then refer back to what happened before. We never want to sample under waterlogged conditions. So rule of thumb, if you can't drive on the paddock, it's too wet to sample it. So we don't want to be sampling when conditions are saturated. The next thing is keeping samples cool. So we really need to be ensuring that our samples aren't sweating or exposed to any heat after they've been taken, because we want to keep that soil in very much the standard condition that we collected it from. Then in terms of sending to the lab, always send express post, and we always send on a Monday or Tuesday. That way it's going to get to the lab within that week. We talk about the requirement to use NATA and ASPAC accredited labs. NATA being the accreditation for quality control of the processes that are used, and ASPAC being the Australian Soil and Plant Analysis Council, which actually is a monitoring program to look at the same test being done at different labs and see what that variation in that test is. I get asked a lot about soil analysis for microbial function or microbial communities. If that's something that you're interested in, then that's something that you could look at. But the key thing that we've found time and time again is the microbes are responding to the environment around them, both chemically and physically, which means that the amount and type of microbes in the system are going to be fluxing all the time. So you get a number or a set of numbers, that set can change after the next rain, or if we get a cold spell or whatever else happens. So it's not really something that we can make decisions on. So as a general rule, we don't tend to do much testing for microbial communities unless you are part of a project or something specifically in that space, because of that high variability. In terms of the labs that we use, Cool Soil is currently using CSBP, and so all our samples go through that lab in south of Perth. What's interesting is that our postal times are quite similar, between sending samples to Geelong to Nutrient Advantage or sending them over to Perth. The other labs which we recommend are just for general usage are Eurofins or APAL over in near Adelaide, and then the Nutrient Advantage lab in Geelong. So of all the soil labs in the country, they're really the three that have a good consistent and quality assured processes in place, and they consistently use the standard methods of analysis that we need. And just for kicks, we talk about two different pH measurements, pH in water and pH in calcium chloride, which we'll talk about in a sec. But the key reason why we shifted from water to calcium chloride is that our water measurements can flux through the season quite dramatically. That's so this is the months of the year down the bottom. Which one's which? June, so days are June and July. So we'll go through there. So it's really looking at what that fluxing is. And we know when we've changed to calcium chloride numbers, that those numbers are a lot more stable. So the method that's used is highly important. All right, now when it comes to soil testing and looking at soil analysis, the key reason why we do this is primarily to look at what's in our system, what are our plants experiencing, and what's likely to be the most limiting factor in that system. So if we don't know what we're dealing with, we don't know where to put our effort, put our money, put our resources to optimize what our plant can see. And so a key way to look at that is looking at this leaky bucket approach, which is historically known as Liebig's law of the minimum, or we talk about the most limiting factor. So what's the key thing that's pulling the rest of the system down? So if, for example, our bottom hole here is pH, but we keep putting nitrogen on, that nitrogen won't flow through to an increase in plant growth. So until we solve for that key limiter, we can't optimize everything else. All right. Now, I've put a lot of words on these slides. And the reason I've done that is to give you something that you can look at for resources later as well. So we'll get this done up as PDF. But what we'll do is I've got a soil test here, and we're just going to go through the key aspects of that test, what it means, and a bit broader information about the properties that we're looking at. So when it comes to a soil test, the two key properties that really give the context for everything else in that system is our soil texture, so our clay content, and then our cation exchange capacity. And in most tests, it's referred to as the ECEC, the effective cation exchange capacity. And that's really the chemical equivalent of the clay content in that soil. So while there's other things in the soil that can contribute to the CEC or the charge in that system, like organic matter can have its own charge, in most of our soils, it's the clay content that's really driving that charge. So when we look at a soil test, particularly when I'm looking at a test that I've never seen before and I don't know the system incredibly well, the first thing I'll look at is the cation exchange capacity. So how much clay is in the system, how much charge and how much buffering does it have? When we look at the numbers that we'd get for our ECEC, the one down the bottom, here it's 9.4. These numbers can range from 1s and 2s in our sands and our loam systems, all the way up to 30 and 40 and even plus in some of our really heavy clays. So it really does overlay the context and the ability of that soil to change chemical conditions. The other reason why we look at this in a lot of our acidic soils is that the CEC presents the buffering capacity. So it's the ability to withstand change. So if we've got more clay in the system and our CEC is higher, then our lime requirement will be higher because we need to put more lime on to punch through that buffering capacity and to create that change in acidity. In terms of how the CEC is measured, we actually measure all the cations, or the dominant cations on the clay, so calcium, magnesium, potassium, and sodium. And in our acid soils, we throw in hydrogen, aluminium, and sometimes manganese to get our full charge. We add all those together to get the sum of cations, and that's what our cation exchange capacity represents. So it's how many cations can be bound onto that surface. All right, so we know what our clay content looks like and our charge. The next thing that we always look at is what our soil pH is. In most of our systems, everything that we do is driven by pH. In terms of what causes that acidity, there's two reasons why our pHs are dropping in agricultural systems. The first is that all agriculture is acidifying. The product removal that we have from the system is actually a net alkali or a high pH removal through those cations. So every time we remove something from the system, we leave that soil with net acidity. So as we get better at farming and we're pulling off more product, that continues to get worse and worse. I've got a table here to show kind of for not every product, but for some of our key products that we take off in ag, how much lime we would need to offset the alkali that we remove from that. So we can see things like a ton of wheat takes off 9 kilos equivalent of lime. If we look at lupins, we're up to 20. We're up to maize silage, we're up to 40. And then one of the worst is lucerne hay. So we need up to 70 kilos of lime to offset every ton of lucerne hay that we take off farm. And that's due to a combination of both the high offtake of that product and the fact we can generally do multiple cuts of that, the high calcium content in that product, and the fact it's a legume. So it's then also contributing to further acidification through that nitrogen cycling piece. So when it comes to the nitrogen story, that also contributes to acidification because our nitrogen fertilizers, a lot of them actually contribute hydrogen into the system. If we're adding an ammonium fertilizer, so NH4, into the system, which gets converted by microbes into nitrate, we're actually leaving behind some excess hydrogen through that system. Hydrogen is acid. So pH actually stands for the potential of hydrogen. So it's that acid that we're bringing in. In terms of our numbers for pH, as a general rule, we talk about when our soil pHs in calcium chloride are less than 4.8, plants are likely to be impacted by acidity. Now, that's a very broad brush approach. So some plants are more sensitive, some of our legumes, particularly more sensitive to pH, and others are more robust. But as a general rule, if we're seeing 5 or below on our soil tests, then we have to start looking at how to manage that. Now, I just want to I'm going to talk about acidity for a sec, even though this is technically just about soil tests, but acidity is such a big deal. The reason why we go from our cation exchange capacity number on our test straight to pH is that if we have an issue with acidity, it is the issue of the system. It constrains everything else that's happening in our soils. Every biological and chemical function in that system is constrained by pH. So if we have that issue, then we can't just say, yeah, I've got acid soils, but my phosphorus is pretty good, or I've got acid soils, but everything else is fine. No big deal. It's just one of many things. It's actually the overarching thing. So we know that although our nutrients become less available under low pHs, the fertilizer that we apply is taken up quite poorly. We get poor rhizobium inoculation of our legumes. We get reduced microbial function, including nitrogen cycling, and we get poor nitrogen mineralization from organic matter. So everything in the system just kind of slows down. As if you were to slow my voice down, then everything else kind of slows down in that system. And we know that if we don't address that pH issue, knowing that pH is a logarithmic scale, so things when you drop a unit or half, a point going from 0.7 to 4.7 to 4.6 to 4.5, we're not talking linear, we're talking a logarithmic change. So it doesn't take long before things really start to go to pot. The other challenge with that is because we have limited plant options, as our pHs get lower, we lose our ability to get our diverse rotation, and we're losing money in yield for as long as we continue to function under those low pHs. What I've got on the right-hand side here is just to show how a lot of our nutrients respond to acidity as well.
We've just got one question there, Cass, from Terry. Terry's asked, what is the pH effect of poultry manure?
Excellent question. The key way, so there's kind of a plus and a minus when it comes to organic materials. So the nitrogen content of poultry manures means that it will contribute a little bit of ammonium into the system. So there's a slight acidifying effect, but organic matter like manures also have charge. So if you can lift the charge a little bit, then you're actually buffering that acidity piece. We know with our organic materials, we can get a bit of an initial uplift in our pHs when we apply them. But then as the microbes break them down, we find that any response kind of flatlines again after a while. So if you consistently apply them, you may get a little bit of a pH benefit. But the flip side is because you're probably improving your soil structure as well, you're adding a little bit more nutrients and you're capturing a little bit more water through better infiltration if you've got more organic matter in the system, then you may actually grow better plants, which then could also have a negative in terms of increasing acidity. So I guess that's the simple answer, Terry. So the key thing to think about with organics is unless you're doing a massive tonnage every year, they're likely to have a transient impact on the system. And if they did have an impact, it's not going to be, in terms of a slight drop in pH, for example, it's not going to be the biggest impact in that system. So take the win of improved structure and water holding capacity and a bit of nutrients, and it's probably not going to be the biggest lever for acidification in the system. Does that kind of make sense?
Yeah, no, that's good. We're not in the level where acidity is a problem, but we can't afford to head down too much further. So
yeah. So look, you'll get a little bit of extra buffering in the system with manures, but look, in your systems, I think any benefit of having them there is going to be a win.
Yeah.
It's not going to cause you to plummet off the cliff in terms of acidification.
Yep. Thanks.
That's all right. All right. Yeah, so that's the pH story. Now, the other part of pH is around aluminium. So we tend to talk with them interchangeably, saying we've got an acidity issue and so we've got aluminium issues. They generally go together, but it's soil type that drives when aluminium starts to kick into play. So aluminium is present in the Earth's crust. It's the third most common element. It's in everything, all of our soils. So it's not a case of aluminium suddenly popping up and becoming a big deal. It's just as our pHs drop, the aluminium responds to that change in pH through increased solubility, and so we get some aluminium coming through into the salt solution. And that's where that aluminium can contribute into detrimental plant growth. The reason why it has an impact on plant growth is that the form of aluminium that's present in low pH soils can come through the plant root into the root tip and actually interfere with cell division. So it actually causes mutations in that root tip, which then means that the cells don't grow properly and we don't get water and nutrient exchange like we expect. So rather than having these beautifully clean, there's really nice white root tips that we expect, we can end up with something like this picture on the right-hand side, which is a wheat root that has been grown under high aluminium conditions. So it's got mutations and it's not really functioning properly. As soon as we add lime into that system and we increase the pH of our soil solution, that aluminium then has that inverse effect and ends up becoming less soluble. So it goes back into that solid phase on the clays and doesn't cause any harm. So that's why it's a straight pH relationship. So when we're looking at that, we want to know what our aluminium's at to say, well, how bad is things right now, or am I where am I on that spectrum? But in terms of management, if we manage for pH, we're going to manage for aluminium. So it's much better just to go, look, let's work on target pHs rather than going, let's just try and bring our pH up enough just so that we're not having too much of an impact with aluminium. If we take it out of play, that's so much better. All right, now as I mentioned, pH is logarithmic. So as our pH drops, our acidity increases, our aluminium comes up exponentially. So it doesn't take much of a drop in pH for our aluminium numbers to go through the roof. So the graph that I've got here is pH on the y-axis and then aluminium percentage on the, sorry, that was on the x, aluminium on the y. And it's really showing the relationship in a lot of soils through New South Wales, sampled for and measured for both pH and aluminium. And we can look at that general trend. So as our pH drops, the aluminium levels come up. The range in aluminium at each pH level is really due to clays and clay mineralogy. So in our really light soils, our sandy soils, clays, aluminium will come through quite quickly. In our heavy clays, it can take down to pH of 4.5 before aluminium starts to kick in. Now that's pretty scary when we're actually looking at heavy clays with the CEC over 30 at a pH of 4.5. That's really showing how much those systems have pulled down in terms of acidity. Excuse me. In terms of our numbers, if you look at greater than 5%, that's kind of where we say that aluminium will be having a significant impact on plant growth. All right, last thing about pH, and just because I can't walk away from a presentation on acidity without talking about our lime strategies. Most of you guys have heard me chat before about the importance of incorporating lime. So if we're applying it, we need to mix it in. The other thing that we find is when we have a history of broadcasting lime, and we go back in a few years' time to sample again to see how our pHs are looking, as a general rule, we find that a pH has increased. We go, sweet, I've applied lime, pH has come up, happy days. What we don't appreciate is that if we look at this image here of 0 to 10, most of our lime which is broadcast is still on the surface. Now, it's not doing anything. When we soil sample, we sample to 10 centimeters, and then we put it in a bag or a bucket, mix it all up, and send it to the lab. The lab is measuring the average pH in that soil sample. It's not determining that stratification. So on the surface, you could be at 7.5, and by the time you get to 10 centimeters, you could be at 4.3 or less. You take it to lab, get the numbers, average pH 5.5, and you go, I've applied lime, it's worked, happy days. Whereas in fact, it hasn't worked. It's merely just been on the surface and has influenced the results that you get. So if you do have broadcast lime in the system, just keep that in mind when you're doing any soil sampling. All right, and the last thing we've got down here is just some evidence to show that incorporation works, which we know it works. This is a replicated GRDC trial that was just finished last year, baselined in 2022, and then different lime rates have been applied. This is just a snapshot of the numbers that we got, but really showing that if we apply 5 tonne of lime, which was to raise it up to 5.8 pH, we bumped up our surface pHs, but we didn't go much below 5 centimeters. When we apply with the shallow disc, we get better effects. When we apply with something a bit more aggressive, we get much better effects. But we have to be really careful if we're using something more aggressive that our soils can handle that. So if we don't know what we can do safely, even the shallow disc is going to do a pretty good job in terms of getting things started. All right, next thing on the list is nitrogen. So we've got 2 nitrogen measures on our test, and these 2 together are what we call our mineral N. So mineral N being what the plant can see. So 10 units of ammonium N and 100 units of nitrate. In terms of our microbial processes, we actually go from ammonium to nitrate from our microbes. We generally start at urea or something else, or our organic N. Some microbes move it through to ammonium and then through to nitrate. So nitrate is the end product in that system. Just for kicks, I've put there the calculation that we use to estimate what our kilograms of nitrogen per hectare would be based on that milligrams per kilogram number. So we've got 110 milligrams per kilogram of mineral N in the system. We calculate that by bulk density and our depth of sampling in centimetres divided by 10. And that gives us 154 kilograms of nitrogen per hectare. So that's pretty good in year 0 to 10. And which it actually aligns well with our organic matter levels. Organic carbon of 2.57 on this test, which is pretty awesome. That's a key reason why we'd have a lot of mineralization happening. Now, we know why nitrogen is important, but a key thing about nitrogen is we know it's mobile. So when we're doing our nitrogen assessments, that deep nitrogen testing is really needed to see what's completely in the system. Phosphorus is, in my mind, one of the key limiters in a lot of our soil systems. A lot of our soil tests are really running quite lean as far as our phosphorus goes. We know it's needed for early growth and vigor. So if we're a bit light on in terms of our rates of P at seeding, that's going to have an impact all the way through the season. P is highly charged, and if we've got any clay in the system, it's going to stick to it. So we don't have to worry about leaching so much with P. It's actually about that immobilized aspect of it. With our test, we talk about Colwell P, and Colwell's the method that we use to provide an estimate of soil P over the season. The key thing to talk about with phosphorus is that our critical levels were done in the 70s to 90s. In the days when our DPIs had the money and resources to do all our rate response curves. They haven't been done under no-till systems. So this means that the levels that we're working with are actually quite inadequate for the systems that we've got. So these were also done under fully cultivated systems, so that it assumes all that phosphorus is uniformly distributed in that 0 to 10 centimetres, which is not under our no-till systems. In our no-till systems, we have stratification of P. So any residue-derived P that comes onto the surface stays there. Then our soil tests pick up that in the same way that our pH tests do and average that through and look like we've got much better results than what we have. So if we're running a 35 Colwell, that's, which a lot of people consider kind of their okay threshold, where the plant or the seed may be seeing 10 or 12. So we can't be running those right on the wire kind of numbers. And just to give us an idea of kind of what this looks like in our systems, we know a 6-ton wheat crop removes about 20 kilograms of heat. So that's 100 kilos of MAP purely needed as replacement in those systems. So just to keep that in mind. The other number with P is around the PBI, phosphorus buffering index, and this gives an idea of indication of P binding. So this number is higher in our clays and it's lighter in our sands. Very reflective of our CEC and our clay content, but then also throws in, if we're in an acid soil, it reflects the aluminium binding P as well. So it's really just if we're less than 100, it's not that bad. For above, we can have these in the multiple hundreds in terms of what that P binding looks like. In terms of potassium, we know it's required for cell wall development. It helps legumes fix nitrogen. And a key part of it is it helps plants resist stress. So if our K levels are on the edge, our plants are going to, have to deal with stresses a bit more. Visual K deficiency takes a long time to kick in. So if we've got any deficiency happening, we can be well down the path of that before we actually can visually see the K's problem. COOL K is, again, the method that we use for K. The key thing about this method is it's not very precise. So while our COOL P numbers, we can say, okay, well, plus or minus 5, so we're pretty much on the money with our P levels. K can be plus or minus 50. So we never take these numbers as a pure critical number that we take to the bank. It's kind of like, well, we're about in that range. All right, key thing with K is that it can be very low in our sandy soils. We don't get visual responses in many systems. There's not a lot of research in the Riverina area on K. And a lot of the early work was done in WA sands. So we do need to kind of choose your own adventure a little bit. Let's say if you're running below 150 milligrams per K, it's worth having a think about test strips or getting some K into the system.
Interestingly, Cass, the GADC updates at the minute so I think Adelaide was the other day and Perth might be coming up, but they are actually now, after a few big crops in WA, K is on the agenda for those guys to be chatting about over there, coincidentally, which is, was something new to some people. It wasn't something they'd previously had to sort of consider. So,
Yeah, no, it's good. There is a new relatively new project that's been going about the last year or two with Nigel Willem over in Adelaide with K. But again, the South Australian and the WA systems, they're very different to ours.
yeah.
But just K is something that can be kind of forgotten about, particularly in our lighter soils. All right, sulfur. Key thing about sulfur is it's required for efficient plant and uptake. So if you're running deficiencies in sulfur and you're throwing on a heap of nitrogen system, your plant isn't going to be able to use that nitrogen well. There's been a heap of research in this space with canola particularly, but the same rules apply in terms of the other crops. If our sulfur levels are low, our nitrogen is not going to be used well. The key part of that is that sulfur, like nitrogen, is used in the production of chlorophyll. So if we don't have S there, then our chlorophyll isn't going to work properly. Potassium chloride, KCl, is the sulfur test that's used. And it does annoy me a bit with some of our tests that they refer to some methods, but not always. But these methods are our standard methods that you'd be wanting to check across labs to see if they're doing the right ones. Historically, we've been running deficient sulfur in our cropping systems. When we moved over from using single superphosphate as our key S source. So something to just keep in mind, in crop we can apply this SOA. If we have any acidicity in the system, or we're looking just to keep some sulfur in the bank, then gypsum's a nice thing just to put on board. In terms of our surface sulfur levels, we generally feel comfortable above 12 or 15. Kind of say, okay, there's enough there for now. But it is quite mobile. So we tend to measure our sulfur when we do our nitrogens at depth through the season as well. Key thing about carbon, this isn't a carbon talk, so I'm not going to dwell on this one because I really want to talk about acidity. But key thing about carbon is it's the product of a good farming system. So we don't look at a carbon number and go, oh, we need to increase that. We look at a carbon number and go, okay, well, does that kind of fit with the system that I'm running? Key things to think about with carbon is the method that we use, W&B. Sounds like WB, hold. It's the Walkley Black method that we use. And the key driver of soil carbon is, first of all, climate. So the Central West guides running more low rainfall zones, that's your biggest limiter. Then it's soil type, with clays being able to hold more carbon than sands. And then our management. So if we have more biomass in the system, we have more inputs into that organic matter. There's some labs that actually report organic matter levels. That's actually just organic carbon times 1.72. So I've taken a bit of the mystery out of it all. But if they just refer to organic matter, They've either done the carbon and they haven't reported it, or they may be a left field lab that has a different technique that isn't aligned with our national standards. The key thing about carbon is it's fluxing. Good years goes up, dry years goes down. It's accumulated through biomass inputs and it's lost through microbial breakdown and nutrient mineralization. So, this is why we get the ups and downs that we do. Conductivity. This is what we call electrical conductivity, EC, which is a measure of the salinity in our soil water. So this is different to sodicity, which we'll talk about in a sec, but it's around the dissolved salts or soluble salts that the plant can see. If we have a lot of dissolved salts in our system, we lose that osmotic potential or that gradient between our root and our water. So if our soil root has a lot of salt in it, which it always does, potassium, calcium, magnesium, if our soil water around that root has low salt, we move water into the root. If that soil water is high in salt, we lose that osmotic gradient and the plant can't take up water and nutrients. So it's really around plants dying of drought, not salt toxicity under our saline systems. Just a heads up, while the main salt is generally sodium chloride in our systems, which is why we measure chloride levels as well, we can also get a spike of EC if we've recently applied gypsum. So calcium, magnesium, potassium, and sulfate are also measured as salts in the EC. So if we've just applied gypsum, there's a fair chance, and it hasn't dissolved and everything yet, fair chance that that'll spike the EC levels. Right. Exchangeable sodium, or ESP, is our sodicity measure. And that's really around the proportion of that cation exchange capacity, which is sodium. So this causes dispersion and crusting and sealing in our conditions, poor water infiltration. And we tend to apply gypsum to solve for that by replacing replacing sodium on the clay exchange with that calcium that brings those clays together and keeps them in good structure. We tend to work on about 6% as our threshold for ESP, at which point we go, yep, there's a fair chance that we're going to get some crusting. Okay, micronutrients. I forgot to get rid of that little image. The micros are something that have as much value in tracking over time as they do in seeing what the actual numbers are. So we know that micronutrients obviously have a key role to play in our plant growth, but that they're less precise when we measure them in soil. And our soil type and region can also have an impact in how well those measures work. So we know every region has key macros that are of concern. Generally, around the Murray, we're talking about copper and zinc as our key ones of concern. Boron deficiency can also be at play, and sometimes a few of others. But that's really the key ones that we look at. So time series testing is a good value for these. And if you think that there's a problem, then plant tissue testing is really where we want to go with micros to make sure that we get a good quality result. All right. Last thing I just wanted to say, after taking you through that kind of speed run of our soil tests, is that the nitrogen interaction is a really key part of that. So whilst we tend to put a lot of our focus on nitrogen and our cost, as one of our single biggest inputs into the system, if we don't have our back of house properties sorted, so our acidity, our sodicity, our other nutrients, if we don't have them kind of optimal or at least adequate in our systems, the plants can't take up the nitrogen the way that we'd like them to. So the whole story is around setting up that package to get that plant firing. And that's it. So sorry we took a little bit longer than expected to take, but there's a bit to get through. So next time you look at a soil test and you think, golly, that's a lot of money for a test, just think of all those rich goodness that we get out of it.
That was awesome. Thanks, Cass. Yeah, no, plenty to digest there. So glad I recorded, so I can probably go back over it when I do get some soil tests in my hands to yeah, see who's who in the zoo in the soil, I guess. And yeah, I put a comment in there. It might be something you guys are interested in. LLS Central West have a podcast called Seeds for Success. It they generally it's I think his name's Rowan. He catches up with farmers around the Central West predominantly, and they recently had a four-part series called Limelight, which really hammers home everything. Cass sort of spoke about pH and liming tonight, about how yeah, the positive response people are getting to it. And yeah, there was one grower, Stuart Tate, I think he was at Mandurama, and he just made the comment lime is a really good fertilizer, because it makes everything that you've got there available. And it was just like a nice way to reframe it in my mind, I think, around yeah, it's a fertilizer, essentially making it all available rather than maybe it being the constraint. So yeah, it just depends how you like to view things, I suppose. But yeah, no, that was awesome, Cass. Has anyone got any questions or thoughts?
Couple of things that go through my mind is that that image you put up as the barrel or the principle of the limiting factor. When I look at a test of mine, there's a lot of things that are low. Is there any sort of formula or what's the best way that you can look at those and the numbers that would be we should look at first?
pH is first, Terry.
Yeah.
So in my mind, I think that's as I hope you've worked out tonight, that's kind of the key umbrella constraint. If you don't have that, the next thing is if you've got any sodicity issues, so stopping your water and oxygen movement into the soil.
Yeah.
So we want to be able to get our water moving. If that's right, the next thing that I would check off is phosphorus.
Yeah.
And the other thing with phosphorus is recently I've discovered that there's a lot of new fertilizer blends on the market for starter P. And just very randomly thinking about that is when you're looking at which, should you go with a certain blend rather than a straight MAP or something, or Granulox Z or whatever, is that granule is real estate. So if there's stuff on that granule that you don't need at sowing, that's taking up real estate that could be occupied by phosphorus or something else. So just really look at your starter fert and make sure that you've got on there stuff that you need and not stuff that you don't. Anyway, that's just a bit random, but yeah, there's some certain blends that they're loading up with sulfur, and you go, well, that's great, but you can apply sulfur very easily at higher levels using other means. So keep that real estate on the granule for phosphorus and sulfur later. Anyway, a bit sidetracked, but yeah, your P levels are something that we're really seeing a lot of limiters in the system. So there's a lot of soil tests that are coming back right on the wire as far as our P. And key thing about P is, if you're doing a lap around your headlands or something, if there's anywhere in your paddock that you're doubling back with your seeding rig, if you're seeing bigger plants in your headlands, then that's generally a P response.
Yeah.
Because if you see more plants, you think, well, that makes sense because I've actually seeded more. But if you're seeing bigger plants and you've got a history of that's the way that you always go, you're loading up that soil with more phosphorus and you're getting bigger plants. So it's telling you that there's something going on in the system. So, yeah.
Yeah. No,
it's super important.
No, that's good. Obviously, P's are terrible in our system. But then I'm considering what fertilizer to use on barley and vetch this year, and the option of going with a MAP. He's going to give me more P, obviously, but it's going to drop the sulfur content down, and my sulfur levels are from 3 to 7. With the majority of 3 to 5. So are we better to load up the single or?
I'd say load up with MAP.
Yeah.
And go half a ton of gypsum.
Okay.
Or SOA after SOA or something.
Okay.
Because your only chance to deliver P in that season is at that seeding point, whereas sulfur is a bit more mobile. So you don't have to have it so you don't need sulfur at the seed right then.
Okay. Yeah.
So even if it's a broadcast light rated gypsum which you could do prior to sowing if you want, or SOA post sowing, which will then give you the salt, because you need good licks of both. But your P is it's so much less about it's not going to move. So you need as much phosphorus as you can right up next to right near that seed. Don't overload it though, because otherwise you'll fry it from the ammonium content. But work with your agro to get your levels, and I would just go hard on your MAP.
Yep.
That seed.
Yeah. No, that's good. Now, the other question that came to mind was nitrogen. Obviously, varies through the year. We're doing this soil testing in, say, February. Come June or May, June, when that plant or needs it, or going into September, what's the variations, just natural variations in nitrogen that we should be taking into account?
The eternal golden crystal ball that I think none of us have the answer to yet, Terry.
Yeah.
But I guess the first thing is around your key time of mineralization of organic matter. So that release of nitrogen from organic matter will be when it's warm still and there's good moisture. So that autumn period. So once things get cold, then that all slows down.
Okay.
So you do get that, but then that slows down, but then the plant starts growing more and is taking more up. And so there's some really good stuff that Geodesia put out around your key timings of nitrogen requirements. So, when the plants hit, half their requirement, 2/3, 3/4 as you go. But the plant will be extracting so you kind of got an accumulation point of mineralization, and you've added urea into the system, and then the plant's taking it up pretty well.
Yeah. No, it's good information.
Paul, you've got your hand up?
Just a question. DAP versus MAP. DAP's very much seems to be on the nose, but I've been to a conference before where it was explained that MAP's actually 4 times more acidifying than DAP, and in terms of the way it breaks down. And typically in the past, we've generally got some free nitrogen with DAP, and pricing wise this year that's changed. But what's your feelings on MAP versus DAP?
So if you take both of those granules and you put them in water, and then you grind them up and you measure the pH, they're both acidic. MAP is more acidic because the process to create the phosphate part of that is by using sulfuric acid, generally in the past and at the moment. Now we're using more phosphoric acid or even nitric and stuff. There's other things that are used. I can't remember that one right now, but it's the creating the phosphate part that actually has the more acid in it. Now, the actual granule is acidic, but when that granule hits soil solution, we very much get a neutralizing process happening. So there's a little bit of play, but actually the longer term thing is that the ammonium component is also contributing to acidity as well through that hydrogen release. But in the big scheme of things, the pH of that fertilizer is not the key driver of acidity in your system. By the time the seed sees it, it's kind of pretty much neutralized. So it's kind of there and we can measure it, and it's, that's great. But once that granule actually breaks down, it very much hits a neutralizing approach. particularly at the rates that we're using, it's not the key issue. There is some work, Harry, I think we've done it, I just can't remember, but actually to say kind of how the different ferts are in terms of acidity. So I'd be happy to throw that in as well into the deck to send out. But yeah, it really is a small part of the full picture. If anything, the amount of urea, if you put it, if you're using urea, Paul, or mostly on?
Oh, not large amounts, but
based?
certainly on canola, and a little bit on wheat.
Yeah.
But yeah, trying to do the things with legumes and that rather than using urea. Yeah.
Yeah. So yeah, urea is much more acidifying, because your rates are so much higher. Yeah, but ironically, even legumes are acidifying as they break down. So they're still going to have more impact than the fert that you're applying. So in terms of choice of MAP versus DAP, if you need that P content, go work on your dollars per unit P as your a key choice.
Yep.
All right. Any other questions?
Sorry, just one more. Is there any alternative to lime for pH? We've just got one paddock, which at the moment it's loosened, so we can't essentially put lime on it and work it in. So, but it's also got some aluminium showing up, which shows interest in your points there. Is there any alternative to lime because it's just so expensive to freight it in?
Unfortunately, no.
No.
So, and you're not that far from Parkes compared to a lot of other guys who are hauling from the Parkes pit. Maybe, Terry, we need to talk about relative cost.
Yeah.
Certainly the freight is a big deal. There is no alternative to lime at this point. And knowing that it's under legumes and you can't work it in. The other thing you can look at, though, is that once you broadcast it, it's not going to move, right? It's not going to blow away.
Okay. Yeah.
So even if you were to apply it when it works for you in terms of logistics and economics, and go, okay, well, look, I know I'm not going to get a great benefit now, but I'm putting it in the bank. And so then when it comes to renovating that paddock at some point into the future, you're not then looking at a massive input of lime or a massive cost.
Okay.
So you've already been parking lime in the system.
Yeah. So would you get any, we've probably got another couple of years before we'd be taking the loosen out. Would you get any benefit in that 2 years?
Once it starts raining lots and lots, we might get a few centimetres of movement next flood. You're kidding, hopefully not. But look, Terry, if you can, in terms of like cash flow and stuff, this is where it gets a bit interesting, because if you've got a bit of cash flow and you can put a bit on, then it's something that you don't have to do later. And yeah, in terms of lime, I don't think it's going to get cheaper anytime soon. Yeah, do what you can now, but mate, have to deal with it later in terms of your cultivation. Yeah. Jane, hi. Are you on mute, Jane? Or volume's not working?
No.
Maybe do you want to? Oh,
Run.
Is that better?
Yes.
Perfect.
I've just changed my microphone. Sorry. Thanks for everything. It's been really informative. Quick question about humates with MAP. Is that anything you have a view on? It might be something for a different day, but any kind of high level thoughts on that? I'm just hearing more and more about it. That's all.
So is it just a product that has kind of piqued your interest a bit, Jane, or do you have
No, just a product one of the guys that does my cropping has been starting to wonder about it. And it's just, so I've been doing a little bit of reading, but we haven't tried it. So I don't know much about it.
So we'll definitely delve into that in detail later on when we talk about the biostimulants and everything. But the short answer is, from a research perspective, we know that a good quality, high carbon material can improve phosphorus availability in acid soils. And we know that because that's actually what my PhD was on a very long time ago. So that's from a very technical perspective, we know that works. But from a reality perspective and the economics and everything else, the rate of increase in P availability you would get it's not knock it out of the park, right?
Okay.
So in terms, so this is where my science hat versus my reality hat comes in. So as an economic decision, you would probably get a similar result by applying 5 or 10% more P, just as MAP.
Okay. Yeah.
And knowing that those products are generally a lot more expensive, the key piece at the moment is just get enough P into the system.
Yeah.
So
Okay.
if you're just rounding up your P rates and not kind of hitting the critical levels, you're not going to get a massive response
for
from
it.
that. Yeah. Look, personally, that's something that I think there are some gains to be made in the future in that space.
Yeah.
But you just, in terms of just making sure you've got enough P for the plant to see, it's not a silver bullet.
Okay. No, yeah, and I'm a bit short of P, and I did get a quote during the week, but it was $80 a hectare for a humate, and I was like, oh, okay,
Bloody
That's-
hell.
quite a lot.
So that comes back fundamentally, Jane, you have to be looking at dollars per unit P. And 80, so what would MAP be running at?
MAP is
Like equivalent on a per hectare basis.
oh, yeah, it's a lot less. Yes, so it'd have to be doing an amazing silver bullet job to warrant it. Yeah.
Yeah. So just work on just building up your P rates.
P. Yeah.
And the beautiful thing with P is it won't move, right?
Yeah.
That's once it's in the soil, like you're never going to lose your money. In a lot of our soils, we do bind up P, but it then P works on a diffusion gradient. So as we continue to extract from our systems, we'll get a little bit coming through. And a high PBI soils, it's kind of very, very slow amounts. In our lower PBI, more loamy soils, it'll come through a bit quicker. But the beautiful thing about P is if you're able to bump a bit extra and you don't use it this year, it's going to be there for later. So there's been a lot of talk about nitrogen banking, but in fact, phosphorus banking actually makes a lot more sense to me because you literally bank it. So if you're just adding exactly what you think you need this year and you're running close to the wire, if you hit that rain event that you weren't expecting, that bumps your yield potential up 0.5 ton, right? But you're running close to the wire and your roots don't have enough phosphorus, you're not going to be able to capitalize on that rainfall. Whereas if your systems are running a little bit of a bank of P, then even like some years when you get lower rainfall, you won't use it all, right? But it's still there for later. And if you can just bring that up, then when you do hit that Goldilocks event and that Goldilocks year, you can actually make use of that phosphorus that you've previously applied. So it's going to work for you.
Yeah, great. I hadn't realized you could bank it. So that's, yeah, thanks, Cass.
That's right. I'm happy to talk about P anytime. All right. Just conscious of time, if there's anything any more burning questions?
And feel free to email anything through to, myself or Cass, of course, and we can address anything at a later date as well.
All righty.
Wonderful. Thanks, guys.
Thank you.
Thank you.
Thanks for coming.
Good.
So hanging out, talking dirt.
Yeah.